In this lecture, we talk about regular differential forms. So the space of rational differential forms on a curve C, this is denoted as omega subscript C. So this is generated by symbols of the form df, where f lies in the function field of the curve. So this is subject to standard relations which we have studied in differentiation. D of f plus g is df plus dg. Then you have product rule, dfg is fdg, gdf, and the differential of a constant is 0. So this differential form, this is written in this form. Omega is summation fi dgi, where fi and gi, they lie in the function field of the curve. So let us give some examples to make this more clear. So on a2, you have bases dx and dy. So notice that this a2 is generated by kx comma y. So a differential form is like this. Phi 3x d of xy would give you use the product rule here, and then you get 3x squared dx, 3xy dx. So notice that this and this, both of them lie in kxy. So on an, the basis is dx1 to dxn. So again, corresponding to an, we have the following ring k, x1, x2, all the way to xn. So on an, the basis is dx1 to dxn. So your differential forms looks like this. So basically what means the functions lie in ring kan. So this is what is k of an. So this was k of a2. So again, this is nothing but direct sum like this. So this is nothing but f1 dx1 plus f2 dx2 all the way to fn dxn. So this is an. So what is omega xu? So this is set of regular differential forms on open set of this variety x. So say you have a affine variety v, which is generated by polynomials g1 to gt. So this is the ideal corresponding to this variety v. So for the differential form, you have this kv dx1 all the way to kv dxn, and in the denominator you take the differentials. So that just means you have a function f1 here, which f1 lies in coordinate ring kv, f2 dx2, f2 lies in coordinate ring kv, and then you have fn dxn, fn lies in the coordinate ring kv. So notice that if f is 0 on v, so that is, say, f basically is taken care of in k of v. F is 0 on v, that it means it has been taken care of here in k of v, because when you construct the coordinate ring, this f would be automatically 0. Then df is also 0, and df is taken care of here. So f is 0 here, and df would be 0 in the part you modulo out. So you have differential form. So this looks precisely what we have seen in algebraic geometry. In algebraic geometry, we had this thing. We had the space. Say if it was a2, you had the space kxy, and then you modulo out the corresponding ideal, and that gives you k of v. And that is precisely what is coming here. And then whatever here you have, you take its differential to get this omega v. So this will be more clear in an example. So say you have v minus x squared in a2. So your k of v, we already know. If it is in a2, this will be kx comma y, and then you modulo out our ideal, which is y minus x squared. And the differential would be kv dx, kv dy, and you take its differential, which is dy minus 2x dx, which comes right here. So again, this kv and kv here is nothing but some function here. You have f1 dx and f2 dy, where f1 and f2 lie in k of v. So another example, so say you have this projective line. You have obvious coordinates x and y. So you have open set u of x, which corresponds to x not equals to 0, and u of y, which corresponds to y not equals to 0. So you divide throughout by x, put y by x as s. Here you divide throughout by y, put this as t. T is to 1 and 1 is to s. So on uy you just have this one variable t, so this is line a1, so you get kt dt. On ux you just have this one variable x, so you get ks ds. So on the intersection ux intersection uy, we basically have this pt dt equals to sum qs ds. Now you can see from, s is y by x and t is x by y, so st is 1. Now since st is 1, we replace this s by 1 by t and this s by 1 by t. So obviously you differentiate it, you get minus q1 by t dt over t square. Now this equation you can rewrite as t square pt dt is equal to minus q over 1 by t dt. If you forget about dt for a minute and you think about it, this lies in the ring kt 1 by t. Now this does not hold in the ring because you have a t square here and everything you have here is 1 by t. So this will not hold, and the only way for this to hold is if both p and q are 0. So global regular differential forms on p1 are just 0. They are trivial. So let us cover a substantial example. So say you have this x, a variety which is defined by this set x cube plus y cube plus z cube equal to 0. So therefore we are writing as vanishing set of this, and this lies in p2. So first you consider this open set u of x, which corresponds to x not equal to 0. So you divide throughout by x, so this 1 comes from x by x cube, and then you have this, and this s you set as y by x, and t is z by x. So you have s cube and t cube for y cube by x cube and t cube for z cube by x cube. So the corresponding ring on u of x is kst modulo out this generating function. So obviously this is kst because ux means x not equal to 0, you land up in affine plane generated by s and t. So this is nothing but 1 is to s is to t. So therefore you have this ring. Now you take this denominator and you have to find its differential, because this is just the ring corresponding to the variety, but we are trying to find this omega x on this set ux. So you take its differential, so 3s squared ds, 3t squared dt, 3 will cancel out, so dt is equal to minus s squared by t squared ds. So in the denominator we were expecting we will have both ds and dt, but dt can be generated by ds. So therefore this ring omega x, this is just one module, ds module. So we were expecting it to be ds and dt module because of s and t, but this dt can be written as a function of ds. So you just have a ds module. So now you look at this open set uy, which is y not equal to 0. So again this becomes y over y cube right here. You divide throughout by y, so x cube by y cube, z cube by y cube. So u is x by y and v is z by y. So again this uy is nothing but a affine plane, which you can see like this. So you divide throughout by y, so you get u1 and v. So uv correspond to the affine plane. So again, just like here, you will have this ring here corresponding to set uy. So this is the on the affine plane. So you are expecting that this will be generated by two things, du and dv. But again you take this denominator, take its differential, 3u squared du and 3v squared dv. So you get dv is minus u squared by v squared du. So again, this is just generated by single module, du modules, because dv you can express as du. So again, this omega x on uy, this is a du module, just one dimensional. But again, us is 1. So notice that this u is x by y. So u is x by y, and you can see this s is y by x. S is y by x. So you have us as 1. Obviously now you can differentiate it. You get u ds plus s du equals to 0. So then you can solve for du. So du is minus u ds by s. So du you can write in terms of ds. So notice that you have a ds module on your set ux, and then you said you have a du module on the set uy. But now you can further see that you do not even need a du. You can do everything by ds. So on ux and uy, you just have this du module. So let us see, can we reduce the differential forms on uz also to du? So again, for uz, you have the corresponding ring KAB A cube plus B cube plus 1. So again, this set is z not equals to 0. You divide throughout by z. So this one is z by z cubed, x cubed by z cubed, y cubed by z cubed. This you get this. Again, this on uz, you have this affine set, which is generated by a and b. So a and b. So therefore you have the following ring. This is the equation coming from right here. So do you take its differential? Again, you get dA is equal to minus b square by a square db. But again, you have vb equals to 1. So on uz, you can say everything is generated by 1 db module, but vb is 1. So because the way we have set up b, b is y over z, and v is right here z over y. So this is 1. So therefore you can take as differentiable v db plus b dv. This is 0. So you can solve for db. You get db in terms of dv. So instead of db module, you can think of it as dv module. But dv itself is in terms of du. So this dv itself is in terms of du. So dv is in terms of du. So you can say that db you can write in terms of dv, but dv you can further write in terms of du. So you just have one dimensional space. So this omega x on ux intersection uy intersection uz is just one dimensional space, and it is just generated by du. So this is one dimensional.